to gain some intuition on what linearity of expectation is, I want us to do this question first. You have 5 different collectible cards. Each box contains exactly one random card. Let's say this is like cereal or something, okay? You keep buying boxes until you have collected all the 5 cards. What is the expected number, EV, expected value rather, of boxes you need to buy? So what it's asking is what is the expected number of trials, expected number of trials, or boxes in this case, really. Let's keep it less general, until you got all 5. Now, just seeing this keyword until, if you have any intuition on random variables, this screams geometric random variable, because there's not a fixed amount of trials. Now, for the time being, this doesn't really tell us anything. It's just a cool fact to note. And now, I'm not going to tell you right away how linearity of expectation comes into this, but let's just do the question first. So in our case, you open up the first cereal box, okay? What are the odds? Say box A, your first box. What are the odds of getting a card you didn't get already? Well, you don't have any, so it's 100%, it's 1. What about the second box? Probability of getting another one you haven't gotten. Well, you already got 1, and there's 5 or 4 more to go, so it's 4 out of 5. Probability of getting the or a third card you haven't gotten. Well, that's just 3 out of 5, because each box has 5 different collectible cards, or can have 5. And you can sort of see the pattern. C, D, E, sort of running out of space here. So we have all the probabilities, but this doesn't really tell us the expected number of boxes unless you know the fact that the expected number of trials for any case is just 1 over the probability. And I will explain this in a different video, but for now, let's just assume this is true. So our first case, let's run a different. So our first case is 1 on 1, which is just 1. Expected number of trials for our second new card would just be, if you flip it around, 5 on 4. And the pattern continues. 5 on 3. 5 on 2. And 5 on 1, which would just be 5. And all we're doing is taking the reciprocal of each of the probabilities here, because the expected number of trials for each case, or for each stage, is just this. Number each stage. Now, what does this do for us? We're trying to find the total expected number of boxes that you need to buy to get all 5. All we know now is the expected number for each new card. Well, this is where linearity of expectation comes into play, okay? It tells us that the total, first let's actually, let's be smart, let's write out our random variable. Let's see, x is the number of trials until all 5. Then it tells us that the expected trials for all 5 is just the sum of the expected number of trials at each stage, which we already calculated. Plus D plus E. And I'm just relating each of these. So this is A, B, C, D, E. And we sum all them up. So 1 plus 5 on 4 plus 5 on 3, so on and so forth. And I already did this question beforehand, so I already know that this is in a fraction 137 on 12, or around 11.42. So let's just say 12 because, we can't open 11 and a half cereal boxes to get all, and if we open 11, then we're not expected technically to get all 5, so we need to open 12. So yeah, it's a very helpful trick for finding the sum of these things. Just to give another analogy here, something more general, maybe not like question based, not specific. Let's use the coupon collector analogy, as I like to call it. These types of questions are called coupon collecting because you're finding, you're finding the expected number of boxes or somethings until you get a number of somethings, okay? So coupon And so as we saw before, the number of trials is just the sum of the trials at each stage. Okay, so let x equal, here, let's actually write it out. So in a more general sense, let x be the number of trials until you collect. Wow, I'm really spacing it out. Until collect k coupons. So we don't even know how much we want to collect, but we can still have a structure on how we would find this answer. And we know that x would also be, well, the number of trials at each stage. So how many trials until we get our first coupon, which is probably going to be 1, plus until our next new coupon, until our third new coupon, until however many we want, until k. Okay, and this is regardless, I'll write this down because it's important, regardless if dependent or independent. So even if choosing or getting our one coupon in this case affected the chance of getting another, it doesn't matter. The linearity of expectation still applies. And if you don't know what these mean exactly, or you don't completely understand, well, it doesn't matter because this happens regardless if this is true or not, right? And uh, another way of seeing why this works is that even though the probability is dependent, or even if it is dependent on what you've seen, the average total is important. The average total, so the sum of all the draws, is linear. So again, it doesn't matter if the probabilities themselves are related or not, or dependent or independent, because the average total, when summed up into x, is what do you call it? Linear. Okay, so that's the linearity of expectation.